Welcome to my presentation on question 5. Question 5 is all about bond force constants. The question is, the element chlorine is known to have two commonly occurring isotopes, 35Cl and 37Cl, present in a ratio of approximately 3 to 1 in favor of 35Cl. An experiment is conducted to determine the force constant of the bond by IR spectroscopy, in which 35Cl bonded to 35Cl is observed to have a stretching frequency of 550 centimeters to the minus 1. Part 1 of this question is by converting this frequency to Hertz, calculate the force constant of 35Cl bonded to 35Cl bond. This is the equation for bond force constants. So V equals 1 over 2 pi multiplied by the square root of k over mu. V is the frequency in Hertz. Mu is the reduced mass in grams per bond to the minus 1. K is the bond force constant in grams per second to the minus 2. First, we have to calculate the frequency in Hertz using this equation. C is the speed of light in centimeters per second, not meters per second. As you can see, this is already in the stretching frequency is in centimeters. Putting these numbers into the equation, we get the frequency in hertz. As you can see, it's to the minus 1, as this isn't just the wavelength in centimeters, it's the wavelength in centimeters to the minus 1. So it's the hertz, the frequency in hertz we've calculated is 1.65 times 10 to the power of 13 hertz. Next, we have to calculate the reduced mass. It's a very simple equation. M1 is just the molecular mass of the first atom, which is 35. M2 is just the molecular mass of the second atom, which is just again 35. So it's just 35 multiplied by 35 over 35 plus 35. This will give us 17.5 grams per mole to the minus 1, but we don't want it in mole to the minus 1. We want it in per bond to the minus 1. So to convert the two, you just divide this by Avogadro's constant. Avogadro's constant is the number of molecules in a mole, so that will just convert the two. This will give us a new value of the reduced mass, which is at 2.907 times 10 to the minus 23 grams per bond to the minus 1. Next, we just put those numbers into the original bond force equation. So here's the frequency in hertz. Here's the reduced mass in grams per bond. Now we obviously want to make k the subject, so we'll have to rearrange this. So firstly, we divide both sides by 1 over 2 pi. Then we square both sides to remove the square root. And finally, to calculate k, we multiply both sides by the reduced mass to make k the final subject, which is k equals 3125002. Sorry, that's 3125025.5 grams per second to the minus 2. Now, to end this question off, in the first part of the question, I calculate the bond force constant using the stretching frequency of 35Cl bonded to 35Cl and the molecular mass of each one of the atoms in that molecule. The bond force constant will be very useful in calculating the stretching frequencies of other isotopes of Cl bonded to Cl. Now in part 2 of this question, we will calculate the stretching frequencies for each of the remaining molecules. That's 35Cl bonded to 37Cl and 37Cl bonded to 37Cl. Now that I've calculated K, we can use this constant to calculate the stretching frequencies for other Cl bonded to Cl isotopes using the same equation from before, but now we don't have to rearrange it. Firstly, I'll look at the 35Cl bonded to 37Cl. Firstly, I have to calculate the reduced mass of the 35Cl bonded to 37Cl, which is obviously very simple. M1 is 35, M2 is 37, making it 35 multiplied by 37 over 35 plus 37, making the answer here 17.986 grams per mole to the minus 1. But we don't want it in mole to the minus 1, we want it in bond to the minus 1. So again, I have to divide that by Avogadro's constant to give us a new value of 2.988 times 10 to the minus 23 grams per bond to the minus 1. Now putting these numbers into the equation, so there's the new reduced mass, and there is K, that obviously we calculate in part 1, to give us the frequency in hertz, which is 1.628 times 10 to the power of 13. Now calculating this into the stretching frequency, we have to use the equation from before except slightly rearranged. It's still C is the speed of light in centimeters per second, so it's 3 times 10 to the power of 10 over 1.628 times 10 to the power of 13, giving us the stretching frequency of 542.666 centimeters to the minus 1. Okay, next we calculate the stretching frequency, the reduced mass of 37Cl bonded 37Cl, which again, M1 is 37, so is M2, so it's 18.5 grams per mole to the minus 1, dividing that by Avogadro's constant to give us that in grams per bond to the minus 1. Plugging these numbers into the bond force constant equation. So there's K, we're in part 1. There's our new reduced mass in grams per bond. This gives us a frequency of 1.605 times 10 to the power of 13 hertz. Converting that into the stretching frequency. Again, using the same equation as before, the same speed of light. That will give us a stretching frequency of 535 centimeters to the minus 1 exactly. So to conclude, the stretching frequencies of these two molecules, for the first molecule, 35Cl bonded 37Cl, it's 542.666 centimeters to the minus 1. And for the second molecule, it's 37Cl bonded 37Cl, it's 535 centimeters to the minus 1. We calculated these using the bond force constant calculated in part 1. Now part 3, final part, state what assumptions you're making which allow this calculation to be carried out. For these calculations to work, we have to assume that the bond force constant is the same for all the different isotopes of chlorine. This means we assume that the bond between 35Cl and 37Cl and 37Cl bonded 37Cl have the exact same strength as the bond between 35Cl and 35Cl. As if the bonds between these molecules have different strengths, then the bond force constants would be different. And if the bond force constants were different, then we wouldn't be able to calculate the stretching frequencies of other isotopes. Thank you for listening.